Alright, get ready for a deep dive. You understand this thing called transport phenomena?
Right?
It sounds pretty complex. Well, it turns out it's all about how things move,
Yeah.
momentum, energy, and even little molecules. Consider us your guides as we unpack these fundamental laws governing movement and discover how they connect in the ways you might not expect.
That's good. What's fascinating about transport phenomena
Yes.
is that it's happening all around us constantly. It's the unseen force behind everything, from the wind blowing outside your window to the way your coffee cools down.
Things like flux, gradient, and transport properties. Can we break those down?
Absolutely. Imagine you are watching a river flow. The amount of water passing a certain point
Okay.
every second, that's essentially the flux.
Okay.
Is the rate of movement or how much of something is moving past a given point.
Okay. So the flux is all about the flow.
Yes.
What about the gradient?
Yeah.
That sounds bit intimidating.
Not at all. Think of a hill. The steeper the hill, the faster you will roll down.
Yeah.
Right? That's because there's a greater change in height
Yes.
or elevation over short distance.
Yes.
That's your gradient. How much a certain property change over a distance.
So a steep gradient means things change quickly,
Correct.
whether it's height, temperature, or even the concentration of those tiny molecules you mentioned.
Exactly. And the last piece of the puzzle is the transport property.
Okay.
This essentially determines how easily something can flow or move through a specific material.
So it's like material willingness to go with the flow?
That's a great way to put it. For example, think about pouring honey versus water.
Okay.
Honey is thicker and flows much slower, right? That's because it has a high viscosity, which is the transport property of momentum.
So viscosity is all about resistance of flow?
Yes, honey is more resistant than water, which explains why it takes forever to get that last bit out of the bottle.
Precisely.
And that's a perfect example of a first law we are going to explore. Newton's law of viscosity focuses on how fluids flow, which is all about the transfer of momentum.
Right.
Okay, now it tells us that the shear stress or the force needed to make the fluid move is directly related to how quickly the fluid's velocity changes over a distance.
Hold on. Can we unpack that bit? Are we talking about the how fast the fluid moving overall? How that the speed changes within the fluid itself?
Excellent question. Actually, it's about how the speed varies within the fluid.
Okay.
Imagine a river flowing, as we have considered it earlier.
Yes.
The water in the center moves faster than the water near the banks, right?
Right.
Have you observed that? Okay. That change in speed from the center to the bank of the river over the width of the river, that's the velocity gradient.
So the more the dramatic that the change in speed within the fluid, the more the force you need to get that thing moving.
You got it. And remember that stickiness we talked about, the viscosity.
Oh yes.
Have you remembered it?
Yes. Yes.
That plays a key role here. The higher the viscosity, the greater the shear force needed to achieve a certain velocity gradient. So, going back our honey example, it takes more force to spread honey on toast than to spread water because honey has a higher
Viscosity.
Correct. It's more resistant to that change in velocity, and that's momentum transfer in action.
Okay, that's pretty slick way to understand how things flow.
Yeah.
But I am curious, does this viscosity thing apply to anything besides honey and river?
Oh, absolutely. It's crucial in all sorts of applications.
Oh, really?
Yeah, think about how motor oil lubricates your car's engine.
Yes, right.
Okay, how blood flows through your veins.
Wow.
Viscosity is a key player in all these processes.
So this seem simple. Concept of stickiness is actually pretty important.
It is.
It makes me wonder what other hidden concentration we will find as we dive deeper into these laws.
Well, let's move from the flow of fluids to the flow of something else entirely, like heat.
Oh, okay.
And that brings us to our next law, which is Fourier's law of heat conduction.
Okay.
Things are heating up. I'm ready to explain you this next law. Okay, this law tells us that heat will flow from a region of higher temperature to a region of lower temperature,
Okay.
and the rate at which that heat flows depend on temperature difference. Yeah, and
Right.
the material's ability to conduct heat, which is called thermal conductivity.
So if I have a piping hot cup of coffee and the room is cold,
Right?
heat will flow from the coffee to the room until they reach the same temperature, and the cup itself, depending on what it made of, will affect how quickly the heat escape.
Precisely.
Yeah.
Imagine you have two spoons sitting in that hot coffee, okay?
Yeah.
One metal and one wooden spoon.
Okay.
Which spoon would you rather grab?
Definitely not the metal one. I learned that lesson the hard way as a kid.
Exactly. That's because metal has a much higher thermal conductivity than wood. It allows heat to flow through it much more easily.
Right.
That's why metal spoon will feel much more hotter than the wooden one, even though they are both in the same coffee cup.
Okay. So the thermal conductivity is like materials heat superhighway.
Exactly.
Some materials are built for speed while the others are more like back roads. That makes me wonder,
Yeah.
are there any materials that are like heat roadblocks where heat can't get all at all?
That's a great question, and it leads us to the concept of insulators. Materials like rubber and foam have very low thermal conductivity.
Right.
They act as barriers to heat flow, which is why they are used in things like coffee mugs and winter coats.
So, understanding thermal conductivity can help us design things that either efficiently transfer heat or effectively block it. That's pretty cool. It makes me appreciate how these seemingly abstract laws have very real world applications.
And that's just the tip of the iceberg. We have explored momentum transfer with Newton's law of viscosity, and now the heat transfer with Fourier's law.
Right.
But there's one more piece of the puzzle, a law that governs how those tiny molecules we mentioned move around, and that brings us to the Fick's law of diffusion.
Alright, let's talk about the molecules that move. I am ready for the Fick's law.
Okay.
What's
Then let's go. Fick's law focuses on mass transfer, which is all about how molecules move from areas where they are highly concentrated to areas where they are less concentrated.
Yeah.
Think about spraying perfume in a room,
Okay, I can picture that. You spray it one spot and the scent gradually spreads throughout the whole room.
right?
But I am guessing there's more to it than just the molecules randomly floating around.
You are right. There's a driving force behind this movement, and that's the concentration gradient.
Okay.
Molecules naturally want to spread out and achieve a uniform concentration.
So it's like they are always trying to even things out.
That's a great way to put it again. And Fick's law gives us a way to calculate just how fast that spreading happens. It tells us that the rate of molecular movement or the molecular flux is proportional to the concentration gradient.
Okay.
The steeper the gradient, the faster the diffusion.
So the bigger difference concentration between two areas, the faster the molecules will move to try and balance the things out.
Exactly. And like the other laws we have discussed, there's a transport property at play here too. It's called the diffusion coefficient. and it essentially describes how easily a particular molecule can move through a particular material.
So some molecules are like marathon runners, while the others are like slow walkers.
Yeah, that's a fun analogy actually. The diffusion coefficient takes into account factors like the size and shape of the molecule
Okay.
and the properties of the surrounding environment.
It's amazing to think about all these tiny molecules constantly moving and interacting around us.
Right?
It makes me realize how much is happening beneath the surface that we are not even notice.
Yeah, it really is. And what's truly remarkable is that although we have been talking about three seemingly different phenomena, momentum transfer, heat transfer, and mass transfer, there's a surprising connection between them, you know?
Now that's what I call true deep dive movement. All my ears are open. What's the connection?
Okay, well, if you look closely at Newton's law of viscosity, Fourier's law of heat conduction, and Fick's law of diffusion, you will notice a pattern. They all follow the same basic formula. Flux equals a transport property times gradient, correct?
Wait a minute.
Okay.
You are right. It's like they are all speaking the same language, even though they are describing the different things. That's pretty mind blowing.
It is. This unified framework is one of the this unified framework is one of the most beautiful aspects of transport phenomena. It highlights the underlying elegance and simplicity of the natural world.
So even through wait.
Okay.
So even through momentum, heat, and mass are distinct entities, the way they move and interact with each other are the same fundamental principles.
Exactly, and this realization has profound implications.
Okay.
You know, it means that understanding how heat flows can actually gives us the insights into how pollutants spread or how fluid moves through pipes. It's a powerful connection.
That's incredible. It's like we have unlocked a secret code to understanding how the world works.
Exactly.
But all this talk about gradient and fluxes, it's still a bit abstract. Can
Okay.
we bring it down to the earth a little? How these laws show up upon our everyday lives?
Let's think about something you probably do every day. Making a cup of tea.
How does a simple cup of tea become a lesson in transport phenomena?
Okay, then first you put the kettle on the stove,
Right.
and then the heat driven by the temperature difference between the stove and the kettle starts flowing from the hotter surface to the cooler one.
Right.
That's Fourier's law in action.
Right.
Okay.
And the material of the kettle matters too, doesn't it?
Yeah,
Like a copper kettle would heat up faster than a ceramic one.
exactly. Copper has a higher thermal conductivity,
Right.
so it acts as a super highway for heat. You gave us the
I
example,
already mentioned
correct?
it.
So it acts. Copper will act as a super highway for heat, letting it flow through much more efficiently. Now, as the water inside the kettle starts to heat up, you'll notice something interesting happening.
You mean those little bubbles that start to rise?
Well, even before the bubbles, if you look closely and you'll see the water swirling around, that's convection. And it's driven by the Newton's law of viscosity. As the water of the bottom of the kettle heats up, it becomes less dense and starts to rise. The cooler, denser water at the pot sinks to the bottom, creating a continuous circulation, you know.
Oh, so it's like a little dance of hot and cold water, all governed by this law?
Yeah, exactly. That's governing law is the law of viscosity.
Right.
And this swirling motion helps to distribute the heat more evenly throughout the water. It ensures that the entire volume of water heats up efficiently. Now, let's say you have poured your hot water into your mug and you added a tea bag.
Yeah.
Okay?
The moment of truth. What's happening at a molecular level when those tea leaves hit the water?
This is where Fick's law takes center stage. You know, the tea leaves contain flavor, molecules that are highly concentrated within the leaves themselves. When they come into contact with the water, those molecules start to diffuse outwards, moving from the area of high concentration to the area of low concentration in the water.
So it's like the molecules are escaping the crowded tea leaves and spreading out into the wide open spaces of the hot water.
Exactly. And over time, as those molecules continue to spread, you will notice that the water gradually changes color and takes on the flavor of the tea.
Right.
That's diffusion in action, driven by the concentration gradient and governed by Fick's law.
Wow, I never realized that the making a cup of tea was such a complex scientific process, like a mini masterclass in transport phenomena.
It really is, and it highlights how these fundamental laws are constantly at play in our everyday lives, even in the simplest of activities.
It's like we have been living in the world governed by these invisible forces and never even realized it.
Yeah.
So, if making a tea is one example, where else these laws come up in our daily routine?
Actually, they're everywhere. Think about cooking a pot of pasta.
Okay.
The heat transfer from the stove to the pot, the water boiling due to convection, the pasta absorbing water and then softening through diffusion. It's all transport phenomena.
All right, you are absolutely right. And what about when you light a candle? The wax melts down due to the heat conduction.
Correct.
The flame flickers because of the convection currents.
Correct.
And the scent of the candle spread throughout the room and takes it the diffusion part. It's mind blowing how much we can understand about the world just by knowing these three laws.
And don't forget about our own bodies. Every breath we take relies on diffusion to transport oxygen from our lungs to our bloodstream,
Right.
and carbon dioxide out.
Right.
The circulation of blood throughout our bodies is governed by the principle of fluid dynamics, heavily influenced by viscosity.
It's like our body are machines, constantly relying on these three laws to function properly. This is seriously making me appreciate the connection of everything. But I have to ask a question. Why should we care about understanding these laws beyond just satisfying our intellectual curiosities? What's the practical significance?
Yeah, that's a great question again. The applications of these principles are truly far reaching. For example, in chemical engineering, understanding transport phenomena is crucial for designing efficient reactors, optimizing heat exchangers, and developing effective saturation processes.
So it's like just a theoretical.
No, it's not theoretical. It has real world applications that impact our lives. In environmental science, this law help us model how pollutants disperse in air and water, which is vital for developing effective remediation strategies and protecting our planet.
And I imagine it's also crucial in fields like medicines, where understanding the fluid flowing in our body is essential for the things like drugs delivery and design the artificial organs.
Yeah, correct. You hit the nail on the head. Understanding how fluids like blood or medications move through our bodies is essential for developing effective treatments, and it goes beyond that. Think about the design of airplanes and cars. Aerodynamics and fluid flow are the key to optimizing their performance and fuel efficiency. Yeah, it's incredible how something as seemingly simple as understanding how things move can have such a profound impact on so many different fields. This deep dive that we have gone through has been a real eye-opener. We came into this thinking transport phenomena was going to be all equations and technical jargon, but it's actually incredibly fascinating and surprisingly relevant to our everyday lives. Now, it's a testament to the power of scientific inquiry, how exploring seemingly complex concepts can lead to a deeper appreciation for the world around us.
It makes me wonder what other hidden connections are out there waiting to be discovered, and how can understanding this fundamental principle help us to solve some bigger challenges in humanity.
Okay, now those are excellent questions, and it brings us to an important point. While we have explored the basic principle of transport phenomena today, the learning doesn't stop here. So here's a final thought. that like thought-provoking question that we can leave our listeners as we wrap up this part of our deep dive. I think a great question to ponder is this: how can understanding these seemingly simple laws of transport phenomena empower us to make a real difference in the world? I love that because it really gets into the heart of why this knowledge is so valuable. Think about climate change.
Yes.
One of the biggest challenges we face is figuring out how to reduce carbon emissions and prevent further warming of the planet. Well, understanding heat transfer is absolutely crucial for developing more efficient energy systems,
Yes.
designing buildings that stay cool naturally, and even predicting how heat will move through the atmosphere and oceans.
So something like figuring out better insulation for our homes is directly tied by the Fourier law.
Absolutely. And by understanding how heat flows through different materials, we can make smarter choices about how we build and insulate our homes to minimize energy waste and reduce our carbon footprints. And it goes beyond just buildings. This knowledge can also be applied to designing more efficient solar panels,
Wow.
developing new battery technologies, and even capturing carbon emissions from power plants.
Wow, it's incredible to think that these fundamental laws we have been discussing can play such vital role in tackling such complex global issues.
It really highlights the interconnectedness of science and engineering. And it's not just climate change. Think about access to clean water. Millions of people around the world lack access to safe drinking water. And one way to address this challenge is through desalination, removing salt from seawater to create fresh water.
I have heard of desalination plants, but I have never really thought about the science behind them. How do the transport phenomena come into their picture and play the role?
Desalination relies heavily on principles of mass transfer. There are different methods, but many involve using membranes to separate the salt from the water. Understanding diffusion and how molecules move across those membranes is essential for optimizing the efficiency and cost effectiveness of these processes.
So, by applying the Fick's law, we can essentially create a clean drinking water from a seawater. That's incredible.
It is, and it demonstrates how understanding these fundamental principles can have a real impact on improving people's lives.
It's amazing to see how something that started as a deep dive into a scientific laws has led us to the conversation about climate change and access to clean the water. It really underscores how science is not just about the abstract concepts. It's powerful tool for solving the world problems.
Yeah, exactly. It's obviously a powerful tool for solving real world problems, and that's the beauty of learning process. The more we understand about the world around us, the more equipped we are to make informed decisions and contribute to a better future.
This deep dive has been a true journey of discovery. We started with a stack of research on the transport phenomena and ended up into some biggest challenges facing by the humanity. It's been fascinating, insightful, and even bit inspiring.
I couldn't agree more. As we wrap up, I want to emphasize that this is just the beginning of your exploration of transport phenomena. There's so much more to learn, so many more connections to make, and countless ways to apply this knowledge into your own life and in the world.
So, to our listeners, we encourage you to keep that curiosity alive. The next time you see the steam rising from your coffee, think about the Fourier's law. When you notice the scent of a freshly baked bread filling your kitchen, remember the Fick's law. And as you marvel at the power of rushing river, recall the Newton's law of viscosity. These laws are not just the equations in the textbook, they are the hidden forces shaping our world.
And who knows, maybe someday you will be the one applying these principles to develop a groundbreaking new technology, solve a pressing environmental problem, or simply make a delicious cup of coffee. Possibilities are endless.
Thank you for joining us on this incredible deep dive into the world of transport phenomena. We hope you have gained a new application for the elegance and the power of these fundamental laws and the countless ways they impact our lives.